Power factor correction then. A higher power factor is an advantage in delivering power more effectively to a load. Consider this RL circuit with the given angle between the current through the resistor and the current through the inductor. Again, we rely on our phasor diagram here to get an idea, of what we're looking at phasorially in terms of the angle. So we've got a simple little parallel circuit here with the current total. You can see we've got a source and our two passive components. The power factor of an inductive circuit can be increased by the addition of a capacitor. So you can see in the circuit now we've added a capacitor. Well, what does that do? Well, you can see it changes the total angle associated with the circuit. Okay, so we've got the current through the inductor. Notice that the current has decreased. The current in the capacitor, though, we're not seeing much there, and we've got our total current out here, almost magnitude-wise in line with IR. The capacitor compensates for the phase lag of the total current by creating a capacitive component of the current that's 180 degrees out of phase with the inductive component. This has a canceling effect and reduces the phase angle and power factor as well as the total current. In an RL lead network is a phase shift circuit in which the output voltage leads the input voltage by a specified amount. The output is taken across the inductor. Recall in the RC lead network, the output was taken across the resistor. So we can see here we've got the output taken across the inductor here and the associated phasor voltage diagram showing that V out leads V in. The angle between V out and V in we're going to designate as the angle phi. We can see that down here. We can see the lead then on V out. V out then is equal to, in the polar form, I, the current, at an angle of minus theta, X sub L at an angle of 90 degrees. We take the product, the difference in the angles. Phi then is 90 minus the inverse tangent of X sub L over R. We invert that to make it positive, the inverse tangent of R over X sub L. So the angle phi between the output and the input then is always positive, indicating that the output voltage leads the input voltage. Looking at an example here, determine the amount of phase lead from the input to the output on the network. So phi is equal to 90 minus the inverse tangent of X sub L over R, and we end up with an angle of 71.6. So in this case, the output leads the input by 71.6 degrees. Determine again the amount of phase lead from the input to the output for this network. The first thing we need to do is convert our inductor 50 millihenries into a reactive term. So we get 314 ohms when we do that. Looking for the angle then, 90 minus the inverse tangent gives us 65.2 degrees. The output leads the input by 65.2 degrees. For the lead network, determine the output voltage in phasor form when the input voltage has an RMS value of 5 volts. Draw the input and output voltage waveforms showing their peak values. Okay, so in this one, the first thing we see here is that we need to convert the inductance to X sub L. So in this case, we've got from the previous examples, we see that X sub L is 314 ohms and an angle of 65.2 degrees. So V out is equal to X sub L over the sum, the phasor vector sum, times Vn and the angle phi. Okay, so when we do that, 314 over the vector sum, 5 times 65.2 gives us a V out of 2.1 at an angle of 65.2. Again, you should recognize these from your days that you learned these expressions for calculating the relationship between V out and V in. They're just now in the form of vectors and phases. So the peak values then of the voltages are, so we rely back on our RMS conversion, 1.414 VN in RMS. So 1.414 of 45 degrees gives us 0.707, and for V out, 1.414 times V out to 2.10 gives us 2.97. So we can see again, we've seen this waveform before, with a lead here of 65.2 and a maximum value in each case, RMS 707 and 2.97. For a lag network, notice we're taking the output across the resistor. So your basic RL lag network, the phasor voltage diagram shows the phase lag between V out and V in. Input and output waveforms again. In this case now we can see that the angle phi is lagging, V out is lagging V in. So in this case we're going to calculate the output phase angle. So for the lag network, phi then becomes the inverse tangent of x sub L over R, or an angle of minus 18.4 degrees. The output lags the input by 18.4. Calculate the output phase angle for the circuit. For this one, again, we need to calculate the inductive reactance. We get 6.28 from our 100 millihenry inductor here. we find the angle phi. Now in this case, 628 by 1.2 or by 1.0 k ohms, we get an angle phi of minus 32.1. So the output lags the input by minus 32.1. The input voltage has an RMS value of 10 volts. Determine the phasor expression for the output voltage. Draw the waveform relationship for the input and output. Okay, so again, in this case, we've got that angle, minus 32.1. X sub L is equal to 628, calculated previously. The phasor expression for the output voltage then is V out is equal to, again, there's that form that we learned again in DC, R divided by the vector sum, in this case of R squared X sub L squared, Vn, and its phase angle. So using the product rules and calculations for this, we end up with 1K, the vector sum, times 10 at an angle of minus 32.1, which gives us V out as 8.47 at an angle of minus 32.1. Okay, so Vn was our 10 volt source. V out, we have a lagging waveform of 32.1 degrees, gives us a RMS value of 8.47. We're going to get more heavily into filters, but here's a quick example of an RL circuit as a filter. If you follow along here, you can see what happens in the filtering as the frequency increases. We go from DC to high frequency, and so we can see in each case the value of the inductor and the resistor is fixed, but we're increasing the frequency, and we can see what happens to the output waveform from 10 volts DC, purely resistive, to 8.47, 1.57, 0.79. So you can see as the frequency increases, the RMS output decreases. As the low pass frequency, as the frequency of the input increases, the inductive reactance increases. Because the resistance is constant and the inductive reactance increases, the voltage across the inductor increases, and that across the resistor decreases. The input frequency then can be increased until it reaches a value at which the reactance is so large compared to the resistance that the output voltage can be neglected because it becomes very small compared to the input voltage. The circuit passes DC completely in this case. So an RL circuit as a filter, then we can see the curve response here. We can see that the voltage in, voltage out relationship, you can see what happens as the frequency increases. Okay, so in this case, the series RL circuit also exhibits a frequency selective characteristic and therefore acts as a basic filter. So in this case, as we move from 100 from DC to 100 hertz to 1000 hertz to a much higher frequency, you can see what happens. We go from DC 0 to 0.63, 5.32 up to and above or at 10 volts RMS. And again, we can see the frequency response curve. As the frequency increases, the um, the voltage response changes with respect to the frequency. Okay, so we have our relationship of V in to V out, where we have a maximum.